Subscribe to the channel and hit the bell. I'm Dragon Megalodon, and we're dialing straight into the mainframe for another explainer. Let's crack this open right now.
So, I gotta ask, is your logic flawless, or is your math about to completely crash the system? Today, we're auditing your foundational logic, those system algorithms we call mathematical functions. Look, if your base code is buggy, the whole architecture just collapses. We need to make absolutely sure your scripts are secure, bug-free, and operating exactly as intended.
Section 1. System Definition, the function protocol. Let's strip away all the noise here. A function is basically just a strict machine operation. It's a super tight algorithm. You feed it an input number, usually our x values, right? And it exactly maps to one and only one specific output number, our y values. One input, one output. No ambiguity, zero confusion.
To really visualize this, think about a real-world analogy. First, we have valid code, the biological mother rule. If you input any person, the system outputs their one biological mother. Every single input maps to exactly one distinct output. Boom, valid function. But what about the alternative? Total fatal error. That's the general mother rule. If the system just asks for a mother, one person could map to a biological mother, an adopted mother, maybe a stepmother. Multiple outputs for just one single input. That breaks the protocol and your code crashes.
Now, when we actually visualize these algorithms on a graph, this strict one output rule is authenticated by something called the vertical line test. It's pretty simple. If you scan a vertical line straight across your graph, it should only ever intersect your data line exactly once. That's a valid execution. But consider a simple circle graph for a second. A vertical line slices right through a circle at two totally different points. Two outputs for one x value? Compile crash. A circle is absolutely not a function.
Okay, let's talk syntax. The standard notation here is f of x. Now, listen closely, because we really need to formalize this so the system doesn't misinterpret our commands. This does not mean f multiplied by x. No way. F of x is the exact syntax dictating what the algorithm outputs. It literally stands for the output value y. So if our function rule is, say, x squared plus 1, evaluating f of 2 means feeding a 2 straight into the machine. 2 squared is 4, plus 1 is 5. The system returns 5. Simple as that.
That brings us right into Section 2, debugging syntax, parsing complex inputs. Because let's face it, we aren't always just feeding our system simple integers like a 2 or a 5. Sometimes we need the machine to process raw, complex expressions like f(a plus 3). So how does the system handle this without totally crashing? It handles it through strict execution steps. Step 1, take your complex input, a plus 3. Step 2, and this is absolutely not negotiable, wrap that entire input securely in parentheses when you substitute it in for x. It becomes a quantity of a plus 3 squared plus 1. Step 3, expand the mathematical block properly. That gives us a squared plus 6a plus 9. And then we just add that final 1, resulting in a squared plus 6a plus 10.
Now, you might be wondering, why am I emphasizing the parentheses so much? Well, check out this comparison. We have the correct syntax, and then we have the absolute most common beginner bug in the wild, dropping those parentheses. If you just write a plus 3 squared plus 1 without them, the system only squares the 3. You get a plus 9 plus 1. Your entire algorithmic logic is now corrupted, all because of one missing parenthesis. You gotta secure those data blocks.
Moving on to Section 3. System boundaries, setting domains and ranges. Every system has operating limits, right? The domain is the entire set of allowed input x values that actually makes sense for the function. The range is the resulting shadow of valid output y values. You really have to know your system's boundaries. To find your domain, you need to isolate and exclude inputs that trigger fatal compile errors. There are two absolute, undeniable laws you must never break. First, division by 0. If an x value makes your denominator 0, you exclude it. Period. Second, you cannot evaluate even roots, like square roots, of a negative number. If an input makes the data inside a square root negative, you gotta exclude that too.
Let's actually debug a complex equation together using these laws. Step 1, check the denominator. If we have x squared minus 4x plus 3, we factor that out, and yep, we have to exclude 3 and 1 so the whole thing doesn't evaluate to 0. Step 2, check the roots. Say we have the square root of 3 minus 2x. That interior logic absolutely must be greater than or equal to 0. Solving that means x must be less than or equal to 1.5. Step 3. We merge these conditions on a number line to find exactly where both rules are totally satisfied.
So what's the compiled output? The safe operating parameters for this specific system are from -infinity all the way up to 1, and then from 1 up to 1.5. In interval notation, we write this with parentheses for excluded boundaries, like the 1, and a hard bracket for included boundaries, like the 1.5. And there it is. That is your clean, bug-free domain code.
All right, next up is Section 4, the Standard Library Core Toolkit Functions. Every great hacker has a library of scripts memorized. In math, these are your toolkit functions. You need to know their visual signatures instantly so you can map out graphical systems rapidly without wasting precious time plotting individual data points.
Let's run through a rapid-fire catalog. Linear, y equals x, gives you a straight diagonal line. Easy. Now for the quadratic, y equals x squared. That creates a nice U-shaped parabola. Notice how the parabola has even symmetry? It's a perfect mirror right across the y-axis. Then the cubic function, y equals x cubed, swings into a curve with odd symmetry, meaning it actually has a 180-degree rotational symmetry around the origin. Absolute value drops down as a sharp V shape with mirror symmetry. And finally, the hyperbola, y equals 1 over x, which blasts out split curves in opposing quadrants. You gotta memorize these shapes.
And we definitely can't forget exponential functions, like y equals 2 to the power of x. Because the variable is literally up in the exponent, every single step forward doubles the output. This dictates those rapid, steep trajectory curves. You'll see this everywhere in massive data scaling and population growth, which is exactly why this specific function is so crucial to mapping out large-scale architectures today. Finally, we hit Section 5, modding the code, executing function transformations. Now that you got the standard library memorized, it's time to learn how to actually hack them. We can mod these base functions by altering their equations to transform their graphs completely on the fly.
Here is the absolute cardinal rule of function transformation. You must pay attention to where the modification actually happens. Modifying the inside of a function alters horizontal properties, the x values. Modifying the outside of a function alters vertical properties, the y values. Keep that locked in. Think of your basic arithmetic operations as specific transformation commands. Adding or subtracting, that translates or shifts the graph. Multiplying or dividing, that stretches or shrinks the geometry of the code. And throwing down a negative sign, that reflects the graph exactly like a mirror. But here is the real hacker secret, the one that catches everyone out. Outside modifications follow direct logic. Subtract 2 on the outside, the graph shifts down by 2. Makes sense, right? But inside modifications operate on reverse logic. It does the exact opposite of what you'd expect. A -2 on the inside doesn't shift left, it shifts the graph right by 2. A horizontal stretch by 1/4, it actually stretches it out by a factor of 4. Always reverse your thinking for those inside x values.
Let's see what happens when we stack these mods together. Say we have the square root of x, and our new equation is -3 times the square root of 1/4 x. Step 1, an inside multiply by 1/4 means a horizontal stretch by 4. Step 2, an outside multiply by 3 means a vertical stretch by 3. And step 3, an outside negative sign means a vertical reflection across the x-axis. Boom! We just sketched a highly complex transformed function instantly, without plugging in a single raw data point. How cool is that?
Master the inputs, respect the boundaries, control the output. If you memorize the toolkit and truly understand how to inject inside and outside modifications, you have total God mode control over any mathematical system.
That is how you execute flawless logic. If you want to understand what the code says before it explodes, hit subscribe. And hey, don't forget to like this explainer. This tells YouTube that technical content is absolutely still alive. Be sure to share this explainer right now with a beginner coder who desperately needs help debugging their math. And you, what did the code say in your project today?